All right, first lecture, how science works. This is chapter 0. It's sort of a preamble in the online book. Sand can be annoying because it is so small and it is coarse and rough and irritating and it gets everywhere. Sand, like all other ordinary matter, is composed of tiny particles called atoms. Atoms are basically the building blocks of all matter. Building blocks of matter. They are truly unimaginably small. If you took a single grain of sand, one little tiny piece of sand, and you counted up the atoms in it, which would take you forever, there are more atoms in that one grain of sand than there are grains of sand on the largest beach in the world. So imagine going to any beach and going and counting every single individual grain of sand. It would take you your lifetime. There are more atoms in one grain of sand. And according to chemists at least, this is one of the greatest discoveries of humankind. Of course, if you ask anyone who's not a chemist, they'll probably tell you something more significant to your daily life at least. So to understand how matter behaves, it's important that we understand how those particles, the particles that make up the matter, the world that we're observing, that we're living in, is based on those small particles and how they interact. So that's what we're trying to get to in chemistry, is how those small particles interact. So atoms and molecules. And molecules are groups of atoms that are stuck together. It's a particular type of group of atom, but we'll get to that later. If we were to look at water, water is made up of 2 hydrogens and 1 oxygen. That's not a friendly color. That's maybe a friendlier color. Okay, 2 hydrogens represented by these white spheres and 1 oxygen represented by this red sphere. If I was to ask you what the shape of water is, you might come up with this thing on the left. More likely, though, you'd come up with something that looks like this one on the right, where the hydrogens are on the opposite sides and the oxygen is in the middle. It's actually the shape on the left, and that's very important. We would not exist if water had the shape of this linear water molecule. If this was the shape of water, none of us would be here. We would not exist. Lots of things about our universe would be different if water was shaped this way versus shaped this way. Small changes can make a really big impact when it comes to chemistry. There is a direct connection between the world of atoms and molecules. The small world, microscopic, submicroscopic world connects with the big world, the observable world. So one of the things that I really like about, especially this class, Intro Gen Chem, is that there are a lot of concepts that connect with our everyday life. I try to point out those applications, those observations when I can, as much as possible, ways where the concepts we're learning in class show up in our real world and where we might have actual physical experiences with them. As chemists, we explore this connection between the small world and the observable world. How can we make better chemicals that help us in our lives? How can we neutralize bad chemicals? There's a popular conception that chemicals are dangerous. Everything you can hold or touch is made of chemicals. It's all chemicals. Chemicals all the way down. You're made of chemicals. Chemicals make virtually everything we come into contact with. The popular conceptions of chemicals limit them to things that might be dangerous poisons or pollutants. That's not true. That is one aspect of chemicals. Those are the ones that often get talked about. But chemicals are also good things like medicine and other pharmaceuticals. Water's a chemical, and we like water, hopefully. If you don't like water, you probably like things that water's in, and there's also chemicals in those things too. So ordinary things are chemicals as well. The water we drink is chemicals. The air that we breathe is a bunch of chemicals. The food that we eat is so many chemicals. Medicines are chemicals, our bodies are chemicals, and chemists are interested in why do those things behave the way that they do. Some chemists study like the cooking process. Some Some chemists study things like the volatiles in wine. Why does wine smell a certain way? Why does it taste a certain way? How does the color correlate to how it tastes? Why does this version of an avocado taste different from this version of an avocado? Like, there's lots of different routes that you can go. They're not all food related. With chemistry, it's a pretty wide, pretty diverse field. I have this picture of pizza because I don't know if it's this way anymore, but when I was in Davis, I went to a Blaze Pizza, which is like a build your own pizza place, right? And up on the wall behind the servers, they have this very incredibly wrong sign. It says no chemicals ever. And obviously I'm still upset about it because it's actually chemicals always. The entire pizza is chemicals. They just mean the popular conception, no dangerous chemicals, nothing that's bad for you. But cheese is made of chemicals. The dough is made of chemicals. The yeast made of chemicals. So there's chemicals in everything, not just bad stuff. Usually people mean the bad stuff. In science, we often use the scientific method. This is a way of learning. It emphasizes observation and experimentation in contrast to what they had before that, which was reason, where they just like, oh, if this, then that, and the other thing. Now we use the scientific method. It is not a rigid procedure that automatically leads to a definitive answer. It's just kind of a guiding framework of a good set of steps to follow. Usually, I think chemists, other researchers, other scientists are not thinking to themselves, okay, I'm in this phase of my scientific method and I need to now move on to this next phase, and then we're going to test some things, and then we're going to move back to this thing, and then usually they're not thinking about it. It's just a practice that we get into. But since we're all relatively new, we're mostly relatively new to chemistry, it's good to talk about it. It has 4 key characteristics, which we'll talk about on the next slides: observation, formulation of hypotheses, an educated guess, testing your hypotheses with experiments, and then potentially formulation of laws or theories. Basically your conclusions, your takeaways, something cool that you found out, hopefully. This is one representation of what the scientific method might look like, where you start with an observation, just something that you notice about the world. You come up with a guess. You do some experiments. The experiments might lead you to make more observations, to come up with a new hypothesis, to rework your hypothesis, and so on and so forth. Our first step is an observation or a measurement. Oftentimes, these are things we can use the scientific method in our own lives. These are often things that we can see with the naked eye. Other times, they rely on the use of sensitive instrumentation. Often in chemistry, we're relying on equipment that costs tens or hundreds of thousands of dollars to be able to make these really precise measurements. Usually, we're going to have some measurement or a description of some aspect of the physical world. So the example, I've used hats before, but I don't really like the hat one, so we'll talk about my sleep instead. I'm tired when I wake up. Even if I get, let's say I get 8 hours of sleep, 9 hours of sleep, I wake up, I still don't feel rested, that would be an observation. This might be something that you've observed yourself. Okay, what can I do about that? We'll find out soon. First, we're going to talk about a more important observation, Antoine Lavoisier, French, from the 1700s, not photographed, painted here. So Antoine studied combustion. He burned things. He had this little contraption. It's a little closed container with glass walls. He'd put stuff in there, light it on fire, fill it up, and he'd see what changed before and after. He observed the mass of the container and its contents did not change during combustion. So before he burned it, after he burned it, no change. That was his observation. Can you imagine just like making a significant contribution to history because you burn stuff? That'd be pretty cool. Okay, after you make some observations, this can lead to the formation of hypotheses. I think I've often heard hypotheses called an educated guess. This is the plural, so it's educated guesses. Something that might explain the observations that we're seeing. A good hypothesis can be proven wrong. So if we use my sleep example, I wake up after 9 hours, I don't feel well rested. If my hypothesis is that there's a magic man that lives in my house that torments me in my dreams, that is not a very good hypothesis. How would I find the magic man? Magic man's a jerk. How would I find the magic man? And how would I prove that he's affecting my sleep? It's not a very good hypothesis. So it's probably not the magic man that lives in my house. He's probably not affecting my sleep, even if he is real. A better hypothesis might be, not for me personally, but like, maybe I have sleep apnea. Maybe I've got a deviated septum in my nose, so I can't breathe well. Maybe there's too much CO2 in my room. Maybe I'm looking at screens too close before going to bed. There's a lot of different things. Let's go with screens before bed. Or need some melatonin. Or magnesium, because those have been pretty hot right now. Fresh air, cold conditions, all these sort of things. Right? These are some hypotheses that we could draw up for how can we improve Mr. K's sleep, which is a matter that's very important and dear to all of our hearts. Lazarus, on the other hand, hypothesized that when he was in that combustion, when he was burning stuff, it involved the combination of a substance with a component in the air. And that's why things weren't changing in the container. Hypotheses get tested by experiments. So we have to run some sort of experiment to figure out if our guesses were correct. Ideally, they are highly controlled. We want to test one variable at a time, if we can, most of the time. If we're concerned with why something's happening, we want to test one variable at a time. We can suss out what the wrong thing is. For example, if I could banish Magic Man to the realm of shadows and darkness, then maybe that would be a way that I could test my hypothesis that Magic Man is interrupting my sleep. That would be a good way to test one variable at a time. More likely, though, I could try no screens before bed, turn my phone off an hour before bed, put it in another room. Researchers say that that helps. I have yet to take their advice. We could also try taking melatonin or taking magnesium 30 minutes before bed, like my student told me last semester. We could try introducing some more fresh air into the bedroom. Ideally, if we're trying to figure out what exactly is the cause, what's contributing to me getting better sleep, we would do one of these things at a time. I'd do it for a month or so, see how I feel, see if I'm getting better. Unfortunately for me, I did not do a highly controlled experiment. I said, I'm going to hop on the melatonin, let me hit the magnesium, and we're also going to introduce fresh air into the bedroom. So I'm not even sure if I'm sleeping better because I haven't set up any metrics to determine that. I think it's maybe working though. But of course, I didn't highly control my experiment, so I don't know which one of those things is contributing to me. I might be wasting my money on melatonin and on magnesium. I could have just opened the window and then I sleep better. Could be the scenario. So ideally, they're highly controlled tests, and they should be designed to validate, to agree with, or disagree with our hypotheses. If you show that your hypothesis, your guess is incorrect, you can modify it, or you can throw it out entirely. So I might say, no, I don't think it's the melatonin, I don't think it's the magnesium, maybe it's the fresh air. Maybe I need to, lock in before bed, put the screens away. If we get a bunch of observations, we get a bunch of experiments that all say the same thing, that may lead to the development of a scientific law. A scientific law summarizes what happens. It can also predict future observations. So an example might be, if I turn my phone off, I sleep better. If I don't eat a quart of ice cream every single night before bed, I sleep better. I don't do that. I do eat a lot of ice cream. Ice cream's good for you, actually. These scientific laws can also be subject to experimental testing. So scientific laws, like with this, if I turn my phone off, I sleep better. Why do I sleep better? Does it say why? No, it just says if I turn my phone off, I will sleep better. That's all it's doing. It's just if one thing, then another thing. If I don't fill my car up with gas, it stops running. It doesn't say why it stops running. Maybe it's magic. But in Lavoisier's case, he developed the law of conservation of mass. This is one of the important bits of information in this slide, in this chapter. Law of conservation of mass. Mass is conserved. It is not created. It is not destroyed. So in a chemical reaction like burning, like combustion, matter is not created. There's no new matter. All the building blocks are still there. It's not destroyed. We haven't eaten any of the building blocks either, or poofed them out of existence. We can also end up with, through many hypotheses, a scientific theory or a model. And these provide an explanation. So it's not just if this, then that, like with our laws, but it actually provides an explanation. It includes the why. A law is more of a what happens, and a method, a theory or a model is the why it happens. So it's a model of the way nature is, and it can often predict behavior beyond the observations on which they were founded. So for example, if my law is if I don't fill up my car with gas, then it stops running after a while. That doesn't say anything about any of your vehicles, should you have them, right? Maybe your vehicle is fine if you don't fill it up with gas. So the theory, the model, might be internal combustion engines, gas-powered cars, run out of gas eventually, and then they can't run anymore because they run on gas. Your electric car, if you fill it up with gas, is just going to smell really bad. Don't put gas in your electric car. Lavoisier's law, the conservation of mass, led to John Dalton's atomic theory. And those years are incorrect. He did not live a Benjamin Button life. Dalton proposed that all matter was composed of small, indestructible particles called atoms. Those are those building blocks we talked about earlier. Building blocks of the world, which is sort of true. So that's the atomic theory. So in summary, about our laws and our theories, our laws state what happens, and our theory tries to explain why things happen. A law can arise from observation. It could also come from hypotheses. Theories also come from hypotheses. Both of these can be proven to be false. In this class, the laws and theories that we are talking about, for the most part, are pretty ironclad, and they're probably not going to get proven false. In other fields, like physics and astronomy, they're a little bit more cutting edge sometimes. Not that they're not cutting edge in chemistry, just not in this class. But more cutting edge research, sometimes laws and theories do get overturned, do get thrown out. I think this even happens in math. So those things can be proven to be false. This has happened several times, and we'll talk about actually some times where things have been proven wrong. And our last slide of the chapter, how to succeed. We've got this quote from Roald Hoffmann, he's the 1981 Nobel Prize winner for chemistry. He said this: "I like the idea that human beings can do anything they want to. They need to be trained sometimes. They need a teacher to awaken the intelligence within them. But to be a chemist requires no special talent. I'm glad to say it. Anyone can do it with hard work." And the with hard work part is important here. There are a lot of details in chemistry. There's some things that you have to memorize. There's lots of critical thinking in chemistry. So there is hard work involved. There's a lot of understanding that you need to be able to really master the subject to get an A or potentially even get a B. For most of us, it's going to look like a lot of hard work, a lot of studying, doing the homework, going to Logan's SI sessions, making sure that we're showing up to lectures, we're asking questions, and all that good stuff. Speaking of questions, any questions about our Chapter 0 material, scientific method, pizza, how to succeed? Yes? I'm not going to test you generally on like history stuff. I might ask questions about like what were some of the ideas in the atomic theory once we get to that, but you don't need to know when these guys died or were born. It's not that important. Other questions?